Good evening. Thank you for joining this webinar. My name is Bhaskar Vairamohan. I am a project manager at the Electric Power Research Institute. I manage process heating related activities, motors and drives, and other industrial energy efficiency projects. So today we are going to look at several aspects of infrared based process heating. What are the fundamentals of operation, where it is applied, and what are some of the case studies that EPRI has done in the past few years, and also some reference material will be provided at the end for your reference. So the agenda for today to cover in the next 40 minutes would be to talk about what are various heat transfer modes and how and where does the infrared heating fits into that mode, IR fundamentals, applications, case studies, some of the energy benefits, and there are some of non-energy benefits which will also be discussed. And then we will have a summary of that. So before going into the topic, just to give you a high-level overview of who EPRI is. EPRI is an independent non-profit organization which primarily works as a collaborative entity to bring together scientists, engineers, academic researchers, industry experts together to solve some of the problems faced by the industry. We have more than 450 members who are all electric utilities, and not only in US but 20% of the utilities are outside of US, so we have a global presence as well. So in this presentation I have focused a little bit on what is happening in the US market. You can draw a parallel to the European market as well. In industrial process heating, the amount of energy utilized by industry in US is nearly one-third of the total energy consumed by all the sectors. Out of that, process heating is about 20% of the industrial energy. Within the 20%, majority of the heating currently takes place by natural gas and other fossil fuels. If you notice in the chart there, only about roughly 12% of electricity is used in industrial process heating. And we are going to talk on how this infrared heating is being a part of the 12% in the electric usage. This may look like a high school physics. What are the various heat transfer modes? Heat primarily can pass to an object through three different ways. First is conduction, second is convection, and third is radiation. Especially if you are camping in a campground, when you are keeping your hand close to that wood fire, that's convection, where the air surrounding the fire is heated and then it comes to your hand. Typically, if you look at several industrial processes heating, the natural gas process is typically convection based. Conduction is the second method where the heat transfer occurs within the medium because of the vibration of atoms. And induction heating is one of the type of conduction. When we talk about the infrared, it is primarily radiation. The heat is transferred by means of electromagnetic waves and photons. And this is what we are going to focus today's webinar on. So once again, looking at the electromagnetic spectrum and seeing where the infrared spectrum falls in the spectrum. We are seeing the visible light, and above the visible light is the ultraviolet, and below the visible light, below the red color is the infrared. And infrared is categorized into three different ways. Call it a short wave infrared, medium wave infrared, and long wave infrared. But anything within 0.76 micrometer to 10 micrometer wavelength is considered to be an infrared spectrum. It is a line of sight technology. When I say line of sight, the object to be heated has to be in front of the emitter. We call the source of the infrared as an emitter. For example, what you see in the box in the right top image, a car paint being cured, and it has to be in front of the emitter. And ideally, an infrared technology is used for heating uh, plain or flat surfaces. Therefore, infrared is not a one solution for all problems, but rather it is a unique feature that could be used in many different applications that have a very flat surface. And looking at the different types of infrared, long wave, medium wave, and short wave, if you look at the response time in this table, short wave has very short response time, which means it can impart the heat very quickly into the object. And also, the source temperature is the highest for the short wave, and the peak wavelength is 1.2 micrometer. Whereas long wave, it takes about 5 minutes response time to get to the object, but still it is more effective than some of the other fossil fuel based heating. Typically, if you go to an airport or outside, dining in a restaurant outside in a patio, you may see some of the roofs have this infrared heating, and that those are typically a long wave infrared heating. How does the infrared transfer energy? Primarily, it uses a law called Stefan's law, and this law states that the amount of energy radiated by an object per unit surface per second is proportional to the fourth power of the absolute temperature of the surface. So, by this law also it is understood any object above the absolute zero emits energy, and if the emitter is at a higher temperature than the object, then the temperature difference to the power of 4 is the amount of energy that is imparted to the object, and that is why infrared could be very effective in transferring the heat to the object. Typical to a visible light, infrared exhibit very similar properties. It can either be reflected or absorbed or pass through that object. And when infrared radiation strikes an object, when it is reflected or transmitted directly, the part does not get heated. The only way a part or an object to get heat or to heat is when the infrared radiation is absorbed by the object. So this absorption is dependent on several factors of the quality and the color and the material properties of the object. One of the interesting things to note is that it does not heat the air in between the source of the infrared and the object. So unlike the natural gas convection oven where air is heated first and the heated air then heats the part, the air is not heated in this case. So this is a very big advantage for infrared. So like I said earlier, emitter is the one that is the source for infrared lighting, and similar to light can be deflected or reflected using parabolic or flat surfaces so that the rays could be the infrared radiation waves could be directed towards the heated object or object to be heated. Now let's look at how infrared waves are generated. If you recollect, um, the energy of the photons, there is an equation called that uses Planck's constant, Planck's law, and it states that energy is given by hc by lambda, where c is the speed of the light, h is Planck's constant, and lambda is wavelength. This tells that energy is directly proportional to 1 over lambda, or it's inversely proportional to the wavelength, meaning if the wavelength is higher, the energy intensity is lower. So that is shown in the graph above, which is also described in the next slide. Electric infrared waves is produced by heating a resistance element or a filament. Typically, this filament is a nickel chromium or uh, some other types of electric resistance. All the emitters generate radiation over the wavelength in a bell-shaped distribution, and typically the peak determines whether it is a short wave or a medium wave or a long wave. As the temperature is higher, typically it becomes the wavelength becomes very short, and it goes to a short wavelength, as you can see in this bell-shaped curve. This graph gives a very clear differentiation between the three types of radiation within the infrared: long wave, medium wave, and short wave. To generate short wave um, radiation, quartz lamp is used, whereas to generate medium wave, quartz tube is used. And for generating long wave, we have a flat panel heating element. As you can see, as the peak wavelength is reduced, the temperature of the emitter is increased from 1000 degrees Fahrenheit to 36 degree Fahrenheit. And so is the energy intensity. As the wavelength reduces or shifts to the left in the x-axis from 10 micrometer to 1 micrometer, you can see the peak energy intensity is increased from 2 kilowatt per meter square to nearly 14 kilowatt per meter square. So that's how this is this is an important characteristic that is used by the IR equipment vendors while determining what type of system they need to build to impart the correct amount of heat to a part. On this slide, what you are seeing is some of the common electric infrared emitter types. The metal sheath elements shown in the top left figure is used of nickel chromium heating wire in an electric insulating refractory, and this nickel chromium is the same heating element that is used even in your iron box to use in your household iron. The reflector lamp is having a coiled tungsten filament, which is the third drawing from the top, and this can be visualized as like a recessed lamp within your house, and this is a very point source compared to the other medium. The tubular quartz lamp and tube shown in C and D are used to create high temperature medium wave to short wave. These are typically used in industry, automobile industry and plastic industry, etc., to heat the part rather rapidly. Shows the characteristics of the electric infrared emitters. One thing I would like to point or take your attention to is the response time, which says the quartz lamp, which is the source of short wavelength infrared, can heat up in just a few seconds, and long wave takes about 180 seconds, which is 3 minutes. And some of the efficiency is listed in this also. The, the efficiency is not the conversion of electric to infrared, but the energy imparted to the thermal heat energy imparted to the electric energy input. It can be very high for short wave and medium wave technologies. When a vendor is designing a system, there are several factors that need to be considered for designing, and some of the critical ones are listed here, including what is the current BTU transferred to the source, from the source to the object, what is the wavelength, what is the distance from the source to the product, and these are all very critical in determining the length and duration of the time the object is exposed to the infrared radiations. Overexposure or underexposure may cause undesired properties for the object. Also, the color of the coating plays an important role. Sometimes, based on the color, the temperature has to be adjusted so the wavelength is absorbed into the material medium. As I mentioned in the beginning, infrared is not one solution for all problems, but some of the challenges could be easily mitigated with a few simple remedies. For example, we said it's a line of sight technology. Sometimes we can use a metal part to conduct the heat through infrared radiation and then transfer the heat from the metal to some other medium if it is needed. Not effective when moisture readily retained is another concern that ma- manufacturers of, or the customers say. Using a combination or a hybrid infrared and a convection oven could find a solution. And as we see some of the case studies, you will see infrared could be, because of the shorter footprint, it could be used in front of the existing oven or on the, as a booster oven to help speed up the process. And so there are several challenges for infrared, but they could have some remedies so we can still use infrared effectively. Chart gives you an idea of what and where electric infrared could be applied in an industry. Anything that you touch and feel in a day-to-day life can be can use electric infrared. For example, food to glass, metal packaging, paper, plastics, automotive, appliances, everything can utilize the infrared for various processes. So the processes are listed on the uh, uh, x-axis, such as activating, curing, drying, etc. And the market segment is in the x-axis, the vertical axis. So this gives an example of where could be applied, and you can see infrared has a wide industrial application. So with that, we covered some of the fundamentals of operation of infrared and also some of the places where it is applied. In the next 10 minutes or so, let's cover some of the case studies that EPRI has worked with that showed not only energy savings but other benefits as well to the customers. Uh, this case study right here shows how an electric infrared booster saves energy and speeds aluminum aging process. This customer makes aluminum wheels of different sizes. So the problem that he had was unable to meet some of the high demands of the industry. So the traditional method was that was used by the customer is has involves three steps. The first step is heating the wheels to 1000 degree Fahrenheit and holding it for 8 hours. And next, the second step is to rapidly cool by quenching the wheel to room temperature. And then the third step is artificially aging the wheels at a 325 degrees gas oven for 30 minutes. So all these three steps has to complete in order for the wheel to come out of the production facility. The bottleneck was found to be the step number 3, where the wheel has to go through two passes through the 300 feet length gas oven in order to be at 325 degrees. So um, this was discussed with the electric infrared vendors, and a new method was formed. They the new method, they still retained the existing gas oven, but a hybrid solution was proposed. In the hybrid solution, the electric infrared heater, a shortwave infrared oven was introduced just before the gas oven. So when after the second step, when the quenching is done, the wheels go back to ambient room temperature of 70 degrees. So the shortwave infrared oven was able to impart heat to the wheels, so it can be raised from 70 degree room temperature to approximately 300 plus degrees temperature. So once the wheel is over 300 degrees, it is now passed through that existing 300 feet gas oven, and it was able to age at the required 325 degrees Fahrenheit, and all this was happening in just one pass instead of going into the second pass. So this has a significant benefit. First, it reduced the bottleneck by and increased the productivity by 2 times. So that was the first benefit. The second benefit was the energy savings of the natural gas side, where originally there was two passes, now it was cut into one pass. So energy used for that full one pass was saved. And there are some times when there are no wheels that are processed by the natural gas oven, and during those times the natural gas oven could not be shut down because of the time taken for it to come back to the set temperature. However, with the electric infrared booster oven, it could be placed into an idling mode where the unit could be dialed down to a very low kilowatt usage. So some of the heater specifications are listed here also. But important thing to note is that the payback was realized in less than 2 years for the customer, and it helped solve their bottleneck, and they were able to increase their production. In another case study, let's look at how um, this electric infrared was used in a pipe fitting plant to cure paint. So you can see that this is not a particularly a flat profile. The picture on the right, you can see it's a tube. So it has several, it has a circular surface area. So um, the initial challenge faced by this customer was traditionally they used natural gas burner and blower system, and always it was closed, shut down due to maintenance issues. Always there was some problems with the burner or something, so it has to be going through some maintenance several times in a month. So when discussing this problem with the electric utility and the electric infrared vendor, they came up with a unique solution. They used 8 medium wave infrared emitters, at each at 12.75 kilowatts, and with the with the help of the 8 infrared heaters, they were able to um, get the same production time without the maintenance issues. So this picture shows the uh, traditional way of doing it, where a part is dipped into a paint tank and then cured through a S-shaped natural gas oven. And in the new process, the natural gas oven was shut down, and then in the existing space, without adding any additional equipment outside. Just within the existing footprint, they installed four on each side to impart heat from both sides, so the paint could be cured. And with just 8 heaters, they were able to get the required curing of the of the coating. So the process did not shut down, and because of maintenance reasons, and the productivity was maintained. And the payback, the customer had less than 1 year payback for this particular application. One of the benefits the plant manager said was that initially they cannot turn off the natural gas burners that are inside these ovens if they want to go out for a break. But because of electric infrared, they can turn it on and off instantly, like turning on a light bulb. It's as simple as that, turning on and off. They were able to shut down the oven if they want to take a break during lunchtime and then come back and resume production immediately without losing any additional time. So those are some of, it's not an energy benefit, but non-energy benefit that was realized in this plant. Um, Another case study that uh, helped the customer is in powder coating. The previous one was a solvent-based paint, and the new one is a powder-based paint. Powder-based paint could be electric infrared could be very effective in curing powder-based paints also. In this particular case, the customer was um, using a traditional solvent-based paint, and this based on the location. They were in Mississippi, where the humidity was very high. So when the traditionally when they had these parts um, cured, and then they put it in a sack, like a sack bag, and then kept it in a warehouse. Because of the temperature and humidity of the southern part of the United States, uh, the the color was the paint uh, becomes soggy because of the heat, and the sack imprinted its pattern on the part. So they had some issues with the quality of the overall part that was manufactured using the traditional way. So when talking about this, the electric utility, which is Southern Company in this case, which is a major utility in the southern side of United States, um, the Southern Company, along with Fostoria, which is the infrared manufacturer, they worked with this customer and making him change to a powder-based facility. And the customer was very impressed with powder coating and saw same or better quality of the product. So um, this process here shows what is the methodology used by this manufacturer. Initially, the infrared drying oven and the infrared powder curing oven and the powder coating booth were not there. So initially, in the previous method, the parts entered through a phosphate wash to remove any rust or other dirt from the part, and then it went through um, a spray painting booth, and then next it went through a natural gas convection oven, and then it was a batch process, so it was sit there for 8 hours to completely, sorry, to sit there for 4 hours to completely get it cured. Whereas the new process, it moved from batch processing to a continuous process. So in the new process, the parts completely cured in just 4 minutes as opposed to previously 4 hours. And because a small infrared oven is used to dry off the water, it saved time in eliminating air dry of the product also. So now they were able to process 400 racks of parts as opposed to 50 racks of parts. So the production went up by 800%. So the plant manager said initially they have to work overtime to complete the orders, but because of the huge productivity increase, they were able to finish all their work from Monday to Thursday, and they could even have a day off on Friday if needed. So some of that benefits are non-energy, but the customer was really happy. He was able to fulfill all the orders on time with excellent product quality, and it used two-zone approach with 80 quartz lamps, totaling about 300 kilowatt of heat passing to this park. And payback was realized less than a year, and the customer was very pleased. So in those three different examples, we can see how infrared could help in energy savings, in increasing the productivity, in having a smaller footprint, in transferring a batch process to a continuous process, and there are so much more other advantages to it. And these are just a few case stories that we could share in the limited span of time. But for each industry, you could find case studies of successful application of electric infrared heating. And this the power density chart shows why infrared is very effective. As opposed to a natural gas based system, the infrared could have a very high power density, up to 30 watts per centimeter square or 300 kilowatt per meter square. So that's the reason why it can effectively transfer the heat to the object and increase the speed of the production line. EPRI did some research and study in the past and found various efficiency ratios if it is for every electrotechnology that is replacing or displacing a fossil fuel technology. In this particular case, uh, the arrow mark should be pointing to the electric infrared heating, where when it displays the direct fired natural gas based technology, the efficiency ratio could be close to 0.5. And in this case, we found electric infrared heating on an average to be 74% efficient, versus a natural gas fired heating at the best having a 35% efficiency. And these efficiencies are um, a BTU input to the heat energy transferred to an object. This is another nice table that summarizes different types of infrared, not only um, electric infrared, but there is a gas catalytic infrared as well, which we have not covered in this case, but it shows what are the different response time possible. As we saw before, electric short wavelength can impart heat in just 1 to 3 seconds, um, and the medium wavelength can transfer in 30 to 120 seconds, and the efficiencies are also listed here. Um, by far the short wave infrared has the maximum amount of power density or the heat flux in 400 kilowatt per meter square, and the wavelength is very critical in the application. Each color has a response. Each color, for example, a red color coating versus black color coating absorbs heat in a different spectral wavelength. So just using one type of infrared will not be sufficient. Care has to be taken on what type of material is used, and the heat and the distance has to be adjusted so the correct amount of heat is transferred to the object. Energy savings with infrared heating. um, Couple of quick highlight on what are the possible energy savings due to infrared, electric infrared. Easy integration is the first thing, meaning it can be an infrared oven could be easily connected to the front end of the existing oven or a back end, so it could be treated as a booster oven to increase the quality of the product, and it can be also have faster processing times by moving from batch process where it has to sit and soak the heat for 4 hours to 8 hours and converting that to a continuous process, so the products come with a different production line speed, so it increases the production speed, productivity of the plant. Quick startup and shutdown also eliminates preheating, which is needed for the natural gas based systems. Uh, Here is an example of how much time it takes to heat the surface temperature from ambient to 300 degrees for various materials. For example, electric infrared could heat and increase the temperature of the wood to 300 degrees in just 8 seconds, and the same would take about 6 minutes for a natural gas convection oven. So this shows different aspects, why the electric technology could be superior in many cases. This is another interesting study. Um, e- uh, Even though electric infrared heating has a good efficiency, it could be still improved in many places by using few of these recommendations, such as the use of reflectors. Sometimes there may be stray infrared waves that may pass through on the side part of the emitter. So having some kind of reflectors, scheduled cleaning, having a zoned approach, meaning having different zones, um, could be possible with electric infrared. Um, and having an advanced control system helps in controlling the temperature profile of the electric infrared oven. And these all steps could improve from 10%, anywhere from 10% to 30% in actual setup. So when I talked about different zoning controls, you can see here there's a top and a bottom, and then zones A, B, and C. So on the right side of the image, you can see the zone control where it says top, bottom, zone A, B, and C. So each zone could be turned on if the part is just a small piece that you want to heat, and you want to heat only on the top side of the oven. You can just turn on top zone A. So all the zone B and C can be excuse me, can be turned off to save energy. So this kind of a zoned approach really helps in improving the energy efficiency. Also, if you notice on the figure on the left, there is width adjustment. So these two, the left side and the right side of the infrared emitters are on wheels, so they can move away or move closer. And this is particularly helpful if a company is heating different sized parts, different width of the parts. So they can be easily accommodated with just moving the uh, left side bank and the right side bank of the electric emitters to the left or right to accommodate different size. So these all the things help in having good control over the heat to the part. And some of the safety considerations, of course, with natural gas oven, you need to have carbon monoxide control, and there are some exposure to carbon dioxide and other combustible gases that is not there in case of electric infrared. But the standard occupational safety and health administration regulations suggest, especially when you are close to the infrared radiation, to have eye and face protection um, all the time, and also um, Google's with goggles with infrared absorbing glass and IR reflecting surfaces should be used. These are some of the steps taken to avoid any radiation or prolonged exposure to infrared radiations. And finally, what are some of the non-energy benefits that we are seeing? No on-site emissions. So electric infrared heating does not have any point of load emissions at the site. That's a big advantage to facility, especially if it is in a non-attainment area where the company has to pass through environmental regulations to pass through to get the certification to run the plant. So it's a big plus point. Better worker conditions, since it is noiseless and no smoke and clean, it provides a better work conditions. Uniformity of temperature. Temperature could be maintained within a plus or minus zero point 0.5 degrees centigrade. Typically, fossil fuel based um, um, system, plus or minus 5.5 degrees C is the controlled temperature band. But however, with the new advent of uh, process control systems, this band is reduced in the recent times. Instant on-off and precise process control. This is a very big benefit for many plants. As I go through these plants with managers, they say because it can be turned on and off instantly, the workers like it very much, so they can take even if they want to go for a smoke break for 15 minutes during a low production time, they can turn off and go out and come back and resume the production. It is not possible with natural gas, because once you turn off a natural gas oven, it takes a long time to come to the stable temperature mode, and you lose time and energy in that. Productivity increase is definitely a plus. We saw low scrap rate and also high quality, um, clean products. This is another a big advantage for customers using powder paint. For example, in a facility which is processing both white color and black color for two different colors for a part, they initially may send 5 white parts followed by 5 parts to be colored with a black paint. And what happens, because of natural gas convection oven, uh, the powder from the white particles can fall into a black object and causes speckles on the black object. Whereas with the infrared, there is no air circulation or air movement needed, so it does not have that kind of an issue. Low maintenance and worker safety are some of the other key benefits that you can find from electric infrared technology. Finally, this table summarizes uh, what are some of the sweet spots for convection oven and some of the sweet spots for electric infrared oven. Especially when a part is a complex structure, and then definitely convection oven has a significant benefit, because it can distribute heat evenly with complex shapes. Whereas with rest of the parts that are flat surface or uh, big and long and circular, definitely electric infrared has different benefits. And intensity can be easily adjusted for different products using electric infrared. So this chart gives a quick overview and summary of where each one could be applied. And there are different reference materials, some of them from EPRI, some of them from national laboratories, and especially the reference number 5 is a good one to have um, electric process heating book is like a Bible where a lot of process heating technologies are discussed. Um, so these are some of the references that you can follow through. And with that, I would like to pause and turn it over to Hans for taking any questions at this moment, please.